So James Webb Space Telescope showed us several things that we didn't expect. One of them is the probability violation in the number of galaxies that rotate in the same direction relative to the Milky Way and in the opposite direction relative to the Milky Way as we see from Earth. So that is JADES, and it's the probability violation is so strong we can even see it with our own eyes. We don't even need to any special tools or any simulation or algorithms. We can just look at it by eye and see that. Let's go one year backwards, back in time, and that is the first image that was released by from James Webb Space Telescope, taken inside the UDF field, which is relatively close to the galactic pole, and that's important. I'll get to that in a minute. But even in that image that was released without um, a lot of information and with a little kind of a vague description of what it is, and we can see fairly clearly that even with our own eyes, that there's a much higher number of galaxies that rotate in the opposite direction relative to the Milky Way compared to galaxies that rotate in the same direction relative to the Milky Way. The details can be found in the paper here. And the analysis was done by uh, a computer analysis. So it's a defined model that determines to put some science in there and define scientifically or mathematically what we consider as galaxies that rotate in the same direction relative to the Milky Way, what we consider galaxies that rotate in the opposite direction relative to the Milky Way. So the analysis can be found in those papers mentioned here in the slide. But again, we can see it with our own eyes. We don't even need anything. We can use computer analysis just to make sure that we can define it, but we can see it with our own eyes. It's pretty obvious. So, and that is again back 2 years back in time. That's from 2022. That was before Webb was even launched. So, and that analysis is with 1.3 million galaxies from a DESI legacy survey. And that is a map of the parity violation in different parts of the sky. What we can clearly see is two hemispheres. Now, that is not a statistical analysis. That is direct observation. So it's not an attempt to fit the distribution of the galaxies into some statistical model, but this is direct observation. So the two hemispheres here are revealed by the direct observation, not by any assumption. We can still see them. The parity violation is inverse in opposite hemisphere. And we can also see that it's fairly close to the galactic pole because we can see that we can kind of see the Milky Way here. That could be a coincidence, or it could be related to the motion of the Earth within the Milky Way galaxy. I will get to that in several minutes. But and that is some other telescopes, so that's the legacy surveys. But in fact, and any possible sky survey that we can think of show the same thing, and the results are fairly similar, maybe not identical. Each of the telescope different footprint, different depth, and other differences, but it's fairly close and definitely within the 1 sigma. So why does this happen? That's the question. And we can explain it by it could be a galaxy brightness bias, something that causes galaxies to have different brightness. Galaxies that rotate in the opposite direction relative to the Milky Way might be brighter than galaxies that rotate in the same direction, and that leads us to see more galaxies that rotate in the opposite direction. And although the number might be the same within statistical error, but we see more galaxies of one kind, which leads to the parity violation. Another explanation, it could also be an anomaly in the large scale structure. And I saw some simulations that show that that is expected, or some simulation, pretty recent. And it could be also related to rotating universe and black hole cosmology. Black hole cosmology, if the universe is the interior of a black hole that resides in a current universe to ours, then that's an interesting theory that has been around since the 1970s, early 1970s. I don't know what to think necessarily about that as an explanation to or an alternative to lambda CDM, but it can explain several things like accelerate expansion of the universe. The That is not in violation at all with black hole cosmology. In fact, it's completely expected according to that. And the obviously the proximity of the between the Schwarzschild radius and the Hubble radius. So that is, I believe, how the theory even started, because some people noticed that the Schwarzschild radius, given the mass of the universe, is very close to the Hubble radius. So that fits that very well. And the third thing here is the rotating universe, because if the universe is in the interior of a black hole, then black holes rotate. We know that they rotate. So if the universe is in the interior of a black hole, then our universe should also rotate. But how do we know that the universe rotates? We don't have a frame of reference. So we might be able to see it by other indication, indirect indication inside our universe, but not through frame references, because we don't have that. So that could be one explanation. But it could be, and that's what I'm looking very deep into right now, that what happens is that we just see more galaxies because they are brighter. So galaxies that rotate in the opposite direction relative to the Milky Way are expected to be slightly brighter than galaxies that rotate in the same direction relative to the Milky Way. We can use some equations here. But according to this equation, the difference is expected to be highly negligible. You can see here the numbers are very small, and that cannot explain what we see. But we need to remind ourselves that the physics of galaxy rotation is not yet fully understood. We don't know. There are some assumptions, obviously, but we don't understand it fully. And the could be other effects that again we're not aware of, and we don't know, but that is the it could be the what we see. But the fact is that we do see more galaxies that rotate in the opposite direction relative to the Milky Way, and that is direct analysis of that with Sloan Digital Sky Survey and Hubble Space Telescopes. Both show that galaxies that rotate in opposite direction relative to the Milky Way in all bands are brighter compared to galaxies that rotate in the same directions. And again, the data are public. You can access it to the papers I mentioned here, and you can test the data, test the experiments yourselves if you like. Same with DESI Legacy Survey. That's with much more galaxies. And we can see again that galaxies that rotate in the opposite direction relative to the Milky Way are brighter. And the difference is not substantial, it's small, but it's statistically significant. It's very consistent across all telescopes. Again, data are available in the paper mentioned below. That's Galaxy Zoo data that was collected a long time ago. We can treat it as third-party data. Again, we can see the same thing in most of the cases. Two of the cases, it's statistically significant. That's something that we can test very easily with a simple query on the through Sloan CAS server. So the Galaxy Zoo data is there, and we can test it very easily. Shows again the same thing. And another interesting observation here is that the difference increases when the redshift gets higher. So when we use galaxies, when we limit the galaxies to a higher redshift, in this case higher than 0.1, then the differences, the brightness differences becomes more substantial. And that is something to look into very carefully. And that's something I'm working on right now. And I'm going to give you some more examples of that. And also, data are publicly available. You can, there's a URL here below. You can go and get to the data and work with it if you're interested. And the next thing is that's not just the brightness, it's also the redshift. And here we can see several experiments, two telescopes here, DESI and DESI Legacy Survey and Sloan Digital Sky Surveys, different data sets, different analysis methods here, all showing that galaxies that rotate in the opposite direction relative to the Milky Way are also have lower redshift compared to galaxies that rotate in the same direction relative to the Milky Way. And that is something that could be related to other observation. I'll get to that soon. Data, all of the data are publicly available. Links, URLs are in the paper that is mentioned below in the bottom line of the slide. We can see it also in third-party data set. These are data set that I didn't collect, other people collected them for other purposes. That's not exactly what they had in mind, but those data sets show exactly the same thing, and you can access those data sets through other sources, not mine, but these are public data sets that anyone can access. And what is also interesting here is that just like the brightness, the difference in the redshift increases, that bias increases as the redshift gets higher. And we can see that that's with HCS. And we can see here that although in all cases the differences in redshift are not huge, these are small differences, but we see a trend, and the trend shows that when the redshift gets higher, the bias in the redshift it grows. It means that galaxies that rotate in the opposite direction relative to the Milky Way, the differences in redshift are higher, gets higher when the galaxies are farther from Earth. Again, data can be accessed in the paper below. There's a URL in that paper. You can access the data from there. And that is new, relatively new. That's from DESI, Data Release 1, and from the South Pole. I haven't released the data yet. I'm still working on it, but it shows something very, very close to what HCS shows. And that is interesting because if there's a bias in the redshift that grows when the galaxies are farther from Earth, that can explain some other observations that can be only explained right now by bias in the redshift. One of them is the Hubble tension, and that's an experiment using shoes data set. And so it's a small data set. What I did, I only used galaxies that rotate in the same direction relative to the Milky Way and repeated the same analysis that they did, and did the same thing just with galaxies that rotate in the opposite direction relative to the Milky Way. And we can see that when you only using galaxies that rotate in the same direction relative to the Milky Way, the Hubble tension disappears. And when only using galaxies that rotate in the opposite direction, the Hubble tension grows. So again, you see the number of galaxies in the left column. So the number of galaxies is not high, galaxies and supernova. So that number is not high. So it's within statistical error. So it's not cannot be considered an ultimate proof here, but it's something to look into because maybe the Hubble tension is related to bias in the redshift, and that can explain that. So these are some summary of some of the papers that were used here. Thank you for listening.